So this video is going to highlight how to calculate net force if forces seem to be or are in different directions other than both right and left or both up and down. And so questions that we would have seen, such as this first box that I have drawn here, where there's 100 newtons pulling up and 80 newtons pulling down, we should be fairly confident right now saying, well, net force equals that big force on top minus the little force on the bottom, and therefore Fnet equals 20 newtons. Done, easy. When you're doing practice on these questions, what has not necessarily been made clear or made of note is that this is the Fnet in the Y direction, the up and down. If you want to call it up and down or the Y or whatever, the up and down direction has a net force of 20 newtons. We did not look at the net force in the horizontal direction. Well, currently there's no forces acting in the horizontal direction, and so the Fnet X, I'm going to call it for the horizontal direction, is, well, there's no forces. Therefore, it's 0. And so currently, since Fnet is 0 in the X direction, we clearly only have this Fnet force. So we calculated that very easily by looking at force on one side minus force on the other, but that's when they're in the same directions. And of course, you can see these other two pictures I have on my screen now, which is what I'm going to get to, seeing that things might be in multiple directions, which might feel like it makes things more complicated. So the way that I'm going to redo question 1 in the way that I want you to start thinking about things when we get into 2 dimensions and things kind of get more complicated. So the way that we do it is to say, okay, I've drawn my free body diagram. These are all of my forces involved. So we can consider Fnet in the Y direction and Fnet in the X direction and say, okay, well, Fnet in the X direction equals force 1 plus force 2, whatever there is. It turns out there's nothing, 0 newtons. Fnet in the Y direction equals, well, one force, positive 100 newtons, plus a negative 80 newtons. Fnet Y equals 20 newtons. And then what we can do is say, okay, what is our overall net force? Yes, when we have a 0, it's easy to say, well, that one doesn't even have anything, so our net force is just in the Y direction, 20 newtons. But what we can do is we add vectors, tip to tail, find the resultant like we've been doing before, and we say, okay, I'm going to draw my Fnet Y first. So there's my 20, there's my 20 Newton Fnet Y. Okay, well, now let me draw an Fnet X, and once I do that, I can draw a resultant. Well, Fnet X, either right or left, is 0 newtons. So my arrow would be 0. So it's literally nothing. Therefore, there, boom, I just drew my X. I just put a point at the tip of this arrow. Now let's draw a resultant. And notice the resultant is the exact same thing as the Fnet Y, right? Like if we had gone to the right, this would have been our resultant overall net force, combined XY direction. But since there was no X direction, it ends up that the Fnet Y is just your overall combined net force. And so we do the exact same thing when we get to question 2. So I'm gonna erase that there. And actually, I'm just gonna erase all of this. And so we do the same thing. We say, okay, I'm gonna consider an Fnet in the X direction and an Fnet in the Y direction. Well, here, my Y direction, I clearly only have one force in the up direction, and there's nothing in the down direction. So currently my Fnet Y equals that, I don't know, I'm going to call it the force applied 1. That's the force going up. And my Fnet in the X direction, well, I have one force currently in the X direction. And so currently I'm going to call that force applied 2. That force applied 2 is the only force, therefore, the net force in the X direction is made entirely of that 80 newtons. And so we can see that Fnet X equals 80 newtons and Fnet Y equals 100 newtons. And then we say, okay, we're still looking for the overall net force. We know that we're both pulling this box. And I imagine if I were to ask any of you, what direction do you think the box would go? Most of you would say, kind of this-ish direction. And you'd be right. This-ish direction is not accurate. We need a mathematical number to describe the direction. Is it here? Is it here? We don't know. And so this is when we add our x vectors and our y vectors, tip to tail, doesn't matter which order you do it in, to find the resultant. And we say, okay, I'm going to do the x first. So we have 80 newtons this way and 100 newtons this way. We've added them tip to tail. Overall, this resultant is our overall combined net force. And of course, you probably already are seeing how to calculate the resultant. It's going to be 80 squared plus 100 squared and square root that. And it turns out this 128 newtons is our overall resulting net force combined in both directions. This is what we're looking for. And then again, when we said the this-ish direction of the arrow, of course, that's not accurate. We need an angle. And of course, you can see already with this, we're going to say, oh, well, I'm going to use this number and this number, and I'm going to do tan theta equals 100 over 80. And let's do that 100 over 80 inverse tan equals 51.3 degrees. And now all of a sudden, we have a magnitude of our force and a direction. The overall net force is traveling 51 degrees, north of east, or with the Cartesian method, it's traveling at 51 degrees. So we've looked at all the forces involved, and we said we've calculated an Fnet x and an Fnet y, and then we added them together tip to tail to make a triangle for the resultant. And these will always make right angled triangles, by the way. And so now we're going to get to one more complicated question, and then we'll end with an even more complicated question just to show you. So again, on this third example I've drawn here, there's only two arrows on there as well. So there's only two forces, and we can say, okay, we can do, again, like before, we got an Fnet y and an Fnet x, and I'm going to start with Fnet y I'm going to start with Fnet x. If we look at this arrow is traveling right and up. We would describe, it looks like it's traveling more to the right than it is up. The arrow looks like it's kind of not very slopey. It's traveling more to the right. Well, what we can do is say, well, I know that's 100 newtons on there. I'm going to erase the one below it. We can actually make a triangle and figure out how much of that triangle's proportions is traveling up. That should be a right angle. And how much of that triangle is traveling across. And so the question, and I didn't put an angle here, I should have, I'm just going to put 20 degrees. A question would give you that unless they wanted you to calculate the angle. And of course, we can figure out these two sides. So let's do it. We're going to use sine to figure out the y side, and cosine to figure out the x side. So I'm going to do cosine first. 100 times cos 20. And so this is 93.97. I'm rounding, but you don't normally want to round. I'm just rounding for the sake of not making this video too long. And then the other side, 100 times sine of 20 is 34.2. And so what you can see is this person pulling that 100 newtons at 20 degrees, most of their pulling is actually to the right, and a little bit of it is pulling up. And so we can actually see, okay, now that we've broken that down, it's essentially like if we were going to say, person A is pulling up with 34.2 newtons, and they're pulling to the right with 100 newtons. Like that. And all of a sudden we see, oh, okay, hold on. We've got a force down, this 80 newtons, and a force up, the 34.2, and they're clearly opposing each other. And there's only one force pulling to the right. There's nothing opposing it. And that's when we get to our Fnet x and our Fnet y. So I'm just going to bring that triangle back, because normally we don't do that. We leave it like this. But by looking at it, we know that this one is to the right, and we know that this one is pulling up. And so we go back into our equation. So I'm going to do an Fnet x. Well, currently this 93.7 is going to the right. There's nothing else pulling to the right, and there's definitely nothing pulling to the left, which means Fnet x equals, you could consider it force applied 1, the first person's force applied in the x direction, which equals 93.97 newtons. Great. Fnet y now equals, well, we've got a force going up and a force going down, and that's going to be a negative 80 newtons because it's down. And so we can just add them together, negative 80 plus 34.2, because remember when we drew them here, they were clearly opposing each other. And so we get negative 80 plus 34.2 4.2 equals negative 48.8. And so this is our net force in the y direction. We do the exact same thing. We're going to add tip to tail. I like doing the x's first. 93.97 plus now it's a negative 48, which means we're going down. Trying to draw it around half-ish the length, 48.8. You don't actually have to draw the negative on the triangle because since it's pointing down, we know. And there is the resultant. And so if I just rewind for a sec before drawing this, if I were to ask anybody, what direction do you anticipate box 3 will go? Everybody will say somewhere this-ish direction. So notice the arrow we've drawn is this-ish direction. So we're definitely on the right track. Then what we do is just we do a squared plus b squared equals c squared. So I'm going to square that number, and I'm going to square 93.97. Square root that answer, and it turns out our resultant, 105.89 newtons, is our resultant net force. It's not our Fnet x or y, it's the combined net force. And then I won't calculate it here because we're going to move on, but then we need to calculate the angle based on, I would recommend using the ones we started with. So you would, actually we'll calculate it here. You're going to do 48.8 divided by 93.97, and then inverse tan of that. Turns out that this is a 27-degree angle. And so we have an actual angle, we have our magnitude of the force, and the angle that this object is actually going to travel in. Then there can be one more step, and it's not going to be really much more complicated. It's just adding an extra number. So I'm going to actually, well, I'll actually just erase that. The last step could be, let's say two people are they dug up a piece of treasure and are trying to drag it away in that down direction, but somebody says, no, that's my treasure. And they're pulling back with, let's say, 60 newtons of force, trying to prevent them from taking it. Well, we'll do the exact same thing, Fnet x, Fnet y, and we say, okay, well, again, we know person A is pulling to the right and he's also pulling up. Well, we knew that was a 93.97, and we knew that was a 48. It was a 34.2. And so we can say, okay, well, hold on now. We knew that this 34.2 was opposing the 80 newtons like before. That's how we calculated this overall negative Fnet y, which we used in our triangle. But now we say, okay, hold on. This person is pulling backwards, opposing this force. It's not opposing the 80 newtons or the 34.2 newtons. It's opposing only the 93 Newton force. And so when we do our Fnet equation, now we're going to do the person pulling right's force, either minus the person pulling left or plus a negative person pulling left because it's in the negative direction. So plus negative 60 newtons. And all of a sudden we have a new net force of 33.97 newtons, which is positive to the right. And so now if we were to redraw this triangle, we now get 33.97 newtons, and this one should be bigger, 48.8. And again, you can find the new resultant exactly the same way, a squared, b squared, c squared, and you can use sine and cosine or tan to find the angle. So the important thing is, when we did the question from box 1, we just said, oh, Fnet equals 100 minus 80, and it's 20 newtons up. Done. But that was knowing by looking at this, and our brains just naturally did it. We knew that the forces are only up and down. Therefore, there's no force in the x direction. So easy, done. Fnet is just a y direction thing. However, the instant we put in two directions like that, or like this, and adding in that, we now have multiple forces in multiple directions. You have to split them up into x components and y components. Then you find your Fnet x, your Fnet y, you add them together like vectors, tip to tail, find the resultant. That's your magnitude, and then you find the angle, and that will tell you the angle the box travels at. The last thing is, and this will take 2 seconds, friction is in the direction opposite of motion. So if this was the overall Fnet, this is the direction the box will definitely move in. Friction, and I'm going to try to draw it, friction travels that way, exactly opposite. So if we had a friction value of, let's say, well, whatever this magnitude is, it's probably going to be like, I don't know, 52 or something. Maybe we would say friction is, well, if we said friction was 52, we'd say, oh, overall then, oh wait, no, we did friction. Well, that was somebody pulling. Anyways, what you can see here is if a question had also tacked on friction, we would know the direction of friction based on the direction of motion. If they had just told us people are going to pull the box this way, what direction is friction? We'd have to still calculate out the direction they're pulling it, and friction is just kind of 180 degrees in reverse of that, just in the complete opposite direction.